Good morning, folks, or good day, wherever you are. Good night. Um, I wanted to show the current state of the compiler. Um, well, we have a tool that builds the compiler, that's processing the grammar file, generating the Bison and Flex files, and then finishing building the compiler. Um, that set of scripts and processes have generated these files. Some of them are generated by the scripts, by the tool/mk script that was run up here. And some, as you can see, were generated by invoking Bison and by invoking Flex. There's a test suite. The test suite has, well, as you can see, a bunch of test cases that are expected to pass. Let's see what else. We, as part of the build, we generate a grammar file to browse as an HTML file. So this is the grammar for the language. To be able to edit the grammar and generate a compiler as the language was being defined, a series of scripts were written that transform a very simple grammar file and a very simple tokens file into the Bison file and into the Flex file with all of the actions required by the Bison compiler generator. So we're going to take a look at that specification file. So first we have a tokens specification file, tokens.spec, and this specifies all of the tokens of the language. Pretty much the tokens of the language are exactly all of the tokens in C plus a few more tokens. One of the additions to the language that was not described elsewhere in the videos is that we have all of the standard operators, but we also have operators that check overflow. They're called the checked operators. So you have all of your standard C operators, but you also have these checked operators that help determine if something overflowed, which is important when you're writing code that is careful about security, that is careful about values wrapping around, and usually those cause programmers to insert the wrong checks. So anyhow, we have all of the normal operators in C plus the checked operators. Anyhow, this specification file is a tokens file together with the grammar file, which are not very clean, are used to produce a compiler. The grammar file is very compact, so it can be edited without much need for screen real estate. The alternatives, you'll see this is a bit in a columnar format, but all the rule names are on the left, and anything that you see indented in columns, for example, this global declaration list and nothing, they're alternatives. The alternatives are separated by tabs, so here I'm moving by tabs in the file. Now, if you can have a rule in a single line, it will be in a single line. If a rule needs more than one line, then it can use multiple lines. So for example, here this inherent declaration has one alternative here, another alternative here, and then a third and a fourth alternative there. So I'm just going to move down the file. Yeah, that is the extent of the grammar. Wherever in the grammar symbols are used, like plus plus or parentheses, star equals, those are the tokens that are expected to exist in the tokens file. Any name-like thing in the grammar that is not the name of a rule, for example, Boyd or Bull or Char, or if we look at statements, for example, return or go to or switch, or if any of those, they're not going to be rule names like a statement is a rule name. So if something is not a rule name, then it better be a token in the tokens file. Otherwise, the grammar is incorrect. Anyhow, that's the grammar file. From that grammar file is when these scripts run is what produced these grammar HTML file that you see here. Of course, a grammar HTML file is easier to read in that all of the alternatives, like the first one we saw, all of the rules are expressed on the left and all of the alternatives are under it as individual lines. And there's a special alternative that is nothing, which means, for example, the scope with global declarations is either a global declaration list or nothing, because there might be an empty file, for example. Alternatives that are in uppercase refer to lexicographical analyzer rules that encapsulate the rules for an identifier, for example, here. So anything in uppercase is a flex rule. As you can see, anything that is actually not a rule name in the HTML version of the grammar are shown. Everything that is a token, whether it's a keyword or square brackets or anything else, the equal sign or the curly braces, they are shown in bold in the grammar. So when you get to the aggregate, struct, and union, and when you get to the various keywords for declarations, they're all shown in bold, meaning they're not other alternatives in the language. But when you get to, for example, an if, you have the rule for an expression or the statement that opens a scope, and else, and then a statement that opens a scope. Anyhow, that is the grammar file looked at that way. If we go here back to this terminal, we can run again the tool that produces a compiler. The language had originally been called C3, so some of the tools used the names C3 instead of COOGL at this time. If we look at the generated files, so these are all of the generated files. As you can see, when we ran Bison, there were a defines file that was produced. So this parser -gen.h. So parser -gen.h here, and then parser -gen.c. And these two, this one and this one, are produced by Bison. And then with Flex, with a lexicographical analyzer, this is the C code that it produces, lexer-gen.h, and the header file that it produces is lexer-gen well, .c, sorry, and .h. So just to make this a bit easier to talk about, I'm just going to put these in a file and walk you through something. So as we can see here from running Bison, so here we're running Bison, I'm going to delete these extra options that don't matter. So here we're producing the, well, here you see this is the header files that are produced, this is the input file, and when we run flex, delete these extra options. This is the header, the C file that it produces, is a header file that it produces, and this is the input file. So here we have the input file. This is produced by the build scripts, by the tool/mk, and this is also produced by the tool/mk build scripts. Then Bison and Flex are run. So if we look here, well, this one is produced by Bison, and this one is also produced by Bison. This one is produced by Flex, and this one is produced by Flex. All the other files there are produced by the scripts. So files produced by the script, by tool.mk, and all of these are produced by the other tool. Together with this one. The reason I'm pointing out that a lot of the compiler is actually generated by scripts and from grammar files is to explain how it is so easy to modify the grammar and just generate the compiler. So, well, it's not particularly interesting to look at what Bison and Flex produce, but we can look at, for example, what the grammar file that we produce is. So let's do that. So here I'm looking at, this is split into two windows, well, two parts in this BI editor. So there's a top part that we were looking at, and then there's a bottom part, which is this grammar gem.bison file. So this is produced by the scripts. First, it's going to have all of the tokens. Then, well, some include files and whatnot, some of the things required, but eventually we'll get into the actual rules that are produced. So from, well, there's an outer rule that is not expressed in the grammar, but a source code file is really a series of scope global declarations and scope global declarations, and followed by an end of file dummy. This is like a dummy token that is used to keep, and all of the comments in the source file are preserved together with the token next prior to which they appear. So if there's any trailing comments in the source file, they're associated with this end of file dummy token. So we preserve all of the comments by tying them to the tokens that follow the comments. So this artificial rule file is really a scope global declarations followed by an end of file dummy. A scope global declarations is either a global declaration list, or here you have an empty rule. This was one of those that had nothing in the source file. I'm going to bring up here the grammar file. So this nothing up here corresponds to this second alternative of global declarations that has a nothing here. Well, in this generated Python file, you can see the C code that is going to be that is produced here by the scripts, and here we have this. We're creating a node for the rule for scope global declarations with the alternative that uses a global declaration list, and here is calling the create to create the object that represents that list, and it's passing the various arguments to it. Anyhow, I don't want to spend a lot of time with this, but I just want to impress on you that all of these are generated by scripts. They're not hand-coded, which makes the compiler much easier to maintain. So that's generated by scripts, all these rules, and then we can also look at I'm going to quit from here. I'm going to go back to the other file. So we just took a look at the grammar gen Python, and then we have a tokens gen.flex, which is the flex file. It's not particularly interesting to look at. You can take a quick look anyway. So here we have what's been produced by the scripts. Some of the rules that relate to some of the lexicographical analyzing, such as these. These are in another file that I didn't show, but these come from another file that gets put together. So the rules for various representations of numbers and floats and whatnot. Now, some of the other, well, I'm not going to spend too much time on this, but there are member functions that are produced by the tools themselves. So, for example, this one is the one that's going to build a parse tree and dump the parse tree and insert entities in the symbol tables, and it also has its corresponding header file here. But let's look at this one. I'm going to make this bigger. So these are going to be the rules for the member functions, really, for all of the rules. So initially we had the file rule. So there's a rule for fixing up. When we're fixing up a file, this is going from a parse tree to an abstract syntax tree. There's nothing really to fix up for a file. But here we have the rule to insert the symbols. Nothing to be done for it, but we recursively, well, we're calling through the member function to insert symbols. Here we're dumping declarations. We're calling the member function to dump declarations, to dump symbols, to dump the symbol table, to dump the input, and to dump the parse tree. So for each rule, you'll see there's a paragraph here. So these are all the member functions that were generated for with their object-oriented dispatch mechanism happening here. Like you can see the object-oriented dispatch here. So that is occurring for each one of the rules. So that was for the file rule. Now, for each one of the rules, we have one of these, and for each one of the alternatives for the rule, we have the actual member functions for each one of the alternatives. So this would be the alternative for the rule file. You can see that. So this is well, the name of the rule. Now, each alternative, so we had two alternatives. One was scope global declarations, followed by the end of file dummy, and this is the create member function for that alternative. So each rule has a series of alternatives. So these would be the alternatives for when we have global declarations, and then we would have the alternatives well, at the bottom for when it's so, for example, when we look at global declarations, again, we have the dispatching the kind of the virtual function for the rule, and the abstract class for the rule, we can call it, and then each one of the concrete classes for the rule will follow. So again, here we have all of this generated code, and well, we're not generating comments because this is all generated by scripts. Anyhow, if you go back to the other file, we also have the rules that turn long lists into tables. So these rules, when they're doing their fix-up, let's get rid of this one to make it easier to read. So these rules, when they're doing their fix-ups, they're going to turn long lists into tables. That reduces the recursion on the compiler. So here you'll see this. Well, so here we have the to dump the symbol table by walking tables, and so let's find the fix-up rule. So for example, my global declaration table fix-up rule here. Anyhow, a lot of source code is produced. As you can see, this is not a great walk through the compiler. But anyhow, just wanted to impress on you that all of these files are produced by scripts based by the grammar, and we're producing tools and whatnot. We want to run the compiler. We can run it very rudimentary. We can run it with test files, like a tests expected to pass. There's also a tests expected to fail. But we can now look at one of these, or we can run it by hand. Well, let's just look at. So here we have a test program that is used to check the syntax of the language. It uses tuples. You probably don't know about tuples, so it's probably not the best example to look at, but we can run the compiler and just dump the parse tree. I run this script to do some amount of demangling, but the parse tree is there. I can't really spend a lot of time walking through this, but we can produce a parse tree. We can show all of the declarations. So here we have an identifier f being declared as a function declaration. So there's a function f being declared, and here would be the arguments to the function. But here we're dumping the symbols kind of by looking at the parse tree. So each one of these things with an arrow is dumping a declaration. So we can dump the declarations, we can dump the symbol tables. So these were all the symbol tables for that scenario, with all of the things in each one of the symbol tables. And now let's see what else we can do. well, there's some debugging that you can do as well. Let's try to do actually a simple example. Let's create a source file. So say you had function int add that adds two numbers and returns a plus b. So when we run that through the compiler, the default action is to just show what it parsed and what it would generate. At this point, there's really no code to change, so the code will be generated identically to C because this is going to be consumed by the compiler. We run it through the parse tree. Let's run it through the manual here. It just fixes some of the output, makes it a bit nicer. So when we look at the parse tree, we will see that we are indeed running the rule file. We're running the rule for global declarations, followed by the end of file dummy. And global declarations is really a global declaration list. Now that becomes a function declaration. Function declaration specifiers, a function declarator, and a function body. So this is the rule, and these are the alternate sub rules that this parsing produced. So the declaration specifiers, because this is no longer a parse tree, this is an abstract syntax tree, it ends up being a type use. The type itself is int. Well, the token for the type happened to have been int. There's a the function direct declarator, which is the declaration ID, left parentheses, a scope for the parameter declarations, the right parentheses, optional arrays. Well, for functions that return array descriptors, we don't have any optional array descriptors being returned. Contracts, an optional inline. So that's a function direct declarator. Well, the actual declaration ID was an identifier. The token was add. This is a function to add. Then we have the token for the left parentheses. They got parsed here. And the things that were within left parentheses are the parameter declarations. So we have a parameter declaration list, which became a table because we ran it through the code. It turns lists into tables. So this is a table because it declares, you remember it had arguments A and B, so here you have arguments with type A, type int, argument A, there's a comma token in the list, then you have the second argument in the table, B, the closing of the parentheses for that, and if we just let this go to the bottom, there's a, here were the arguments and here is the code. So well, there were no optional array declarators, there was no contract, there was no vital, no required, no promise, no inline, but here we have the body of the function with the curly braces. Again, this was parsed as a return statement. Well, what was within the curly braces was function statements. A function statement is a list, but it didn't even get turned into a table. There was because there was a single statement. So this return statement becomes well, a return token followed by an optional value and a semicolon. The token was returned, and then the add expression is the add expression plus the plus a token and a multiplier expression. But the actual ending of the parsing is A and B. There's really not a multiplicative expression there. This is how the parse tree gets turned into an abstract syntax tree. If you look at the grammar, well, the parse tree for this would have been much more complex. If we dump the symbol tables, so here we have the first declaration. It was a function declaration. We're dumping the symbols, sorry, not the symbol tables. So the first declaration, which is shown here, where we're declaring add, is a function declaration. Each declaration is going to be indented to the left. So here we have the next parameter declaration. I'm going to let this scroll. So we had a function declaration up there. Then we have the parameter declaration. Of course, as part of the function declaration, there's a whole type where the signature for the function has to include the type. So that's why it's also including the arguments A, and the arguments b as part of the function declaration add. Here we have the parameter declaration again declared here. The token is this, but now we're declaring a parameter. And here we're declaring the other parameters. So we have three declarations in this whole function. If we show the symbol tables, then here you have the symbol tables. In the global declarations, there was one symbol add, but then within that, within the scope of the parameter declaration list, we have a symbol table with two entries, A and B. Anyhow, that is a quick walk through the compiler. There's the tools that actually produce this are a bunch of scripts. They're not particularly big. Let's sort them so you see that. So these scripts are really small, but they produce a lot of the code that transform the grammar from a specification file, this one, and from the tokens file into all of those other things that we saw that were generated. Of course, there's more source code than meets the eye. Not all of it is generated. Anyhow, we can look at the whole compiler once it's been put together by running it under cscope. So when the compiler runs, well, here you have whoops. Here up here you had the usage statement that we saw earlier, and here the compiler is doing its work with its arguments and eventually calling the parser. To call the parser, we end up calling into the generated Bison parser, but depending on what we're doing, we're either dumping the tree, so we can call the rule on the file to dump the tree, or we're dumping the symbol tables, we call the rule on the file to dump the symbol tables, or sorry, the symbols, or dump the symbol tables, or just to dump the file. So if we were to follow, I don't know, dump the symbols, then we're calling it on the root of what's been parsed for this file. So again, this goes via dispatching, and the dispatching at this point would be calling dump syms for the file, rules, so we'll be calling here. Anyhow, if you walk through this, you can see how all of this is happening. Let's see. These are all the test cases, the ones that are expected to pass and not pass. We can, I'm going to concatenate them all together. But so we have a lot of test cases. When we build a compiler, we're running some benchmarks at the end. Oh, sorry, when we run the test cases, we run some benchmarks at the end. The scripts are obviously not very fast. Each one of those dots that you see there is running a script. Eventually, I'll be rewriting all of that in Python or something else, but the scripts are in pretty good shape. Here, we're kind of trying to see which of the scripts takes the longest. So when we run the scripts, we're kind of measuring the time each one of them takes. And at this point, the one that does some of the generation of the rule names for the Bison is the one that takes the longest. Anyhow, when we run the tests, at the end, it runs a compiler against a file that has 100,000 plus lines of code, and does a benchmark on that. I'm At this point, they're running a bit slower. I'm capturing the screen, and QuickTime is encoding these things, but all of these run in half a second. Now this is a file with 100,000 lines that that is being used here. I don't know if you hear in the background, this MacBook Pro has got the fans going because QuickTime is probably using a lot of CPU. Anyhow, all of these usually run in less than half a second. It's either just run a compile. At this point, it's just building the parser and outputting the parse, the generated code. Then we have dump the parse tree, or dump the symbols, dump the symbol table, and run it without pruning. Anyhow, I'm going to stop QuickTime and see how this recording went. I appreciate your help and your patience listening to this not very well organized walk through the computer.